In this video, we are going to do some review of vector spaces and subspaces. So recall that a vector space is a set. So there could be some objects in it like vectors or polynomials, but it needs to have two operations. I need to be able to add things together, like be able to add vectors together. And I also need to be able to multiply the things in it by scalars. So multiply by real numbers, for example, like multiply like a vector by 5 or multiply it by -2. And the key thing that a vector space needs to do is satisfy this list of 10 properties. Okay, so I won't focus too much on the 10 properties in this video. We've talked about them more in class. I just want to remind you, what are some examples of vector spaces? So one example was Rn. Rn is the set of all vectors that have n entries, where each of the entries is a real number. Another example we saw was Pn. Pn, this was the set of polynomials, I'm just going to abbreviate, polynomials of degree at most n. So their degree could be n or smaller than n. Another thing that we had mentioned, but we haven't seen an example of it until I'll do one in this video, is m subscript n times n. This is just a notation for the set of all n by n matrices. So the set of n by n matrices. Okay, so with each of these sets, like this thing, all the n by n matrices, or Pn, all the polynomials of degree of at most n, I can do things like add stuff together. I can add two matrices together, add two polynomials together. I can also multiply them by scalars. And it turns out they satisfy all 10 of these properties. Like, for example, the first property says, if you take any two things that are in your set, it still needs to be in the set. Like for the set of n by n matrices, if I take an n by n matrix and I add it to another n by n matrix, well, it's still gonna be n by n. It's still gonna be n by n. And that's what the first property says. Okay, and it turns out that the other ones will be satisfied as well. In general, it's rare to get a problem that will ask you to check if something is a vector space or not, just because you have to check so many properties, and that's often tedious. You might get a problem where it asks you to check, just a couple of the properties. It might specify a few for you to check. What you will get a lot more problems of is, how do you check if something is a subspace or not? So let's review that. So a subspace of a vector space, let me draw a picture. So if I have a vector space, I'm going to denote it by this circle V. The subspace, I'm going to call it H, is a subset of V. So H is a subset of V. It's within V. Then it needs to satisfy three properties. The three properties it needs to satisfy is whatever the zero vector is, that's got to be in H. That's got to be in that green region. H is closed under vector addition. And what that means is if you take any two vectors that are in H and you add them together, that needs to stay in H. That needs to still be in H. And it also needs to be closed under scalar multiplication, which means if you take any vector in H and you take any scalar, any real number, and you multiply them together, that's still got to be in H. Okay, so subspace is a subset of a vector space, and it needs to satisfy these three properties. And that's a much shorter list for us to have to check than having to check all 10 things of a vector space. So if I need to show something is a subspace, we must show that it satisfies all three of these properties. Okay, on the flip side, if I want to show something is not a subspace of a vector space V, we just need to find one property that fails, one property that doesn't happen. Okay, so in terms of our core standards, this topic is aligned with the standard V1. V1 is about determining whether a given set is a subspace of a vector space using this definition, meaning like checking these three properties. All right, so let's do some examples where we practice this. So the example says, for the given vector space, determine whether or not H is indeed a subspace of V. So part A says V is P3. So we're using this notation that we saw up above. This is the vector space of all polynomials of degree at most 3. So, something like t squared minus 7t, that's in P3 because its degree it's not bigger than 3. It's at most 3. That's definitely in P3. But if I did something like t to the 4, well, that would not be in V because its degree is too big. Okay. All right, so then what is H? H is a set, and the things that are in H are P of t. So P of t is in P3. So that means we're talking about polynomials. Polynomials in P3. Polynomials that have degree at most 3. Remember this colon means such that. So now we're about to describe some properties of these polynomials. So this polynomial PT, it's got to have this form. It's got to look like something times t cubed plus something. Okay, and then comma, it has to satisfy this other property, that a minus 2b equals 0. So these coefficients, a and b, need to satisfy this other condition. Okay, so let's get a feel for what types of polynomials are in H. So here's one polynomial, P1. So first off, it's got the right degree. The degree is 3, so check mark. That's not bigger than 3, so that's good. And the other thing I need to check is, does it have the right form? Well, yeah, it does look like something t cubed and then some number. It's totally fine for that other number, the b value, to be negative. So it's got the right form. Cool. And the other thing is, I got to check, does it satisfy this condition, that a minus 2b equals 0? Well, the a is 8, and then minus 2b, you know what? I'm realizing there's a typo. I meant for this to be a plus. Okay, actually, I meant for both of these to be a plus. I meant for this to be a plus and this to be a plus. Okay, so let me just fix that right now. Okay, so my a value is 8, and if I do minus 2b, so 2 times 4, I do get 0, just like the condition says I need to. Nice. So this first polynomial satisfies everything that I need to be in H. So this is a polynomial that's in H. Awesome. What about this second polynomial here? Okay. So first off, is the polynomial in P3? Well, its degree is 2. And that's still good, because that's still less than or equal to 3. Check mark. Degree is totally fine. Does it have the right form? Does it look like this? Well, not quite. Not quite. The form it needs to have is something t cubed and then plus a constant term. Like, this has a t squared term, but that's not allowed. So I'm going to say incorrect form. Or no, sorry, I'm going to say it doesn't have the form that we need. It doesn't have the form at cubed plus b because of the presence of this t squared term. Okay, so as a result, this polynomial, put a slash through that symbol, that is not in, it's not in our set H. Okay, so the things that are in H, they look more like this first polynomial. They got to have this form, something t cubed and then some constant term. And the coefficients, they need to satisfy this condition. A minus 2b has got to be 0. So let's check the 3 conditions that we need for something to be a subspace. So 3 conditions. First, I got to ask myself, is 0 in H? So is 0 in H? Okay. You know what? I forgot to give you all an opportunity to try this. All right. So I think we're at a good point here because we're ready to start tackling the example. This was all just kind of like getting familiar with what the question is saying. So let's do a pause for about 3 minutes to try this. 4, 3, 2, 1. Pause the video for about 3 minutes to try this. All right, so hopefully you did that. Hopefully pause it for about 3 minutes. Let's talk about it together. So by 0 here, because we're talking about polynomials, we mean the 0 polynomial, which is p of t equals 0. So it's the p of t equals 0 for all t. That is the 0 polynomial. The graph of that polynomial is, well, that's the graph of y equals 0. That would just be a horizontal line. That would be a horizontal line on the x-axis. That's the graph of this polynomial. So is that in H? Well, the degree is good. The degree is not bigger than 3. Okay. Does it have the form that we need? Does this look like something t cubed and then plus something plus some constant term? And the answer is yeah, because I could pick both of these things to be 0. So that works. It's got the right form. And then I got to check, does it satisfy this condition? So comma, let's check that it satisfies that condition. So the a, the coefficient of t cubed, is 0. Minus 2 times b, the constant term, is also 0. Oh, and that does equal 0. Awesome. So let me just separate out this stuff I was doing on the side before. Cool. So it satisfies all the conditions that I need for H. So that means, thus, this polynomial, the 0 polynomial, is in H. Is in H. I'll put a check mark. This first condition holds. 0 is in H. The second thing that I need to check for something to be a vector space is it's got to be closed under addition. So closure under addition. Technically, I'll say closure under vector addition. Okay. We don't have vectors here. We have polynomials. But all that means is if you take two things in H, meaning if you take two of these polynomials that are in H and you add them together, well, you still end up with a polynomial that's in H. Let's check that. So let's let P of t and Q of t be polynomials in H. What does that then mean? Well, that means that they both have that form. P of t looks like a t cubed plus b, and same with Q of t. I can't pick the same constants for Q, because then I would be assuming that they're the same polynomial, but I got to pick them to be any arbitrary polynomials in H. So maybe I could call it ct cubed plus d. So I'm taking two polynomials that are in H, and they need to satisfy this condition. So a minus 2b has to be 0, and same thing for the other polynomial, c minus 2d has got to be equal to 0. Okay, now I need to see, well, when I add them, is that still in H? So if I add them, I get P of t plus Q of t. I'll add them. So I'll get the first polynomial, at cubed plus b, added to the second one, ct cubed plus d. Okay, yeah, I can reorder this to put the like terms together. I'll get a plus c times t cubed, and then plus, I can put the b plus d together. So, okay, the degree is still good. This is still a polynomial in P3. It's still got the right form. It still looks like something times t cubed plus a constant term. What's left for me to check is, well, do the coefficients satisfy this? So let's check that. And if I do the first coefficient, which is a plus c, and then I do minus 2 times the second coefficient, which is b plus d, I'm really hoping that that will equal 0. Well, let's simplify this. This, if I rearrange it, becomes a minus 2b plus c minus 2d. And we know from here that both of those portions are 0. We know that this is 0, and this is 0. Nice, so this whole thing equals 0. Okay, so this condition for the coefficients is satisfied. All right, so I get to say thus, when I add them together and I do P of t plus Q of t, well, that is an H. That is an H, so check mark. Awesome. Cool. All right, so I'm running out of room here a little bit, so I'm going to try to shift my work up a little bit. We got one more condition. We got one more condition to check here. Let me also move this up a little bit. I can also move up this maybe a little smidge more. All right, one more condition to check, which is that closure under scalar multiplication. Closure under scalar multiplication. Gotta check that. So when I check closure under scalar multiplication, now what I do is I need to take some arbitrary polynomial, just one this time. That's an H. And I gotta take some arbitrary scalar. I'm gonna call it C. So C is gonna be a real number. Okay, and I'm hoping that when I multiply them together, I'll still get a polynomial that's an H. Well, just like before, I get to say that P of t looks like at cubed plus b, where the a minus 2b equals 0. It's got to satisfy that condition of the coefficients. And now let's multiply this by c. So c times P of t. If I distribute c to each term, I'll get CAT cubed plus CB. Okay, that's still got this form, something t cubed, and then a constant term at the end. Degree is still good. Let's check if the new coefficients satisfy this condition. And okay, let's check it. So I take the first coefficient, which is CA, and then I gotta do minus 2 times the second coefficient, which is CB, and I'm hoping that that will be equal to 0. Well, I can factor a c out of each of these terms. C factored out, and then a minus 2b. But we know what a minus 2b is. That's right here. That was 0. Okay, so this a minus 2b, that is going to be 0. C times 0 is 0. Awesome. So these coefficients, the CA and the CB, they do satisfy this condition. Okay. So thus, c times multiplying my polynomial by a scalar still keeps it in H. I'll put a check mark. So all three conditions hold. Because all three conditions hold, that means this set H is a subspace. Is a subspace of V. I should add a little sentence about a little phrase about since all three properties, sorry, I'm running out of room here a little bit. Since all three properties hold, H is a subspace of V. All right, cool. Let's look at some more examples. All right, let's do some where our vector space is a set of matrices. So let's let V be this thing, M subscript 2 by 2, which means it's the set of all 2 by 2 matrices. Okay, and H is a set. What's in the set? I got a 2 by 2 matrix. It's saying it's an element of M 2 by 2. That's 2 by 2 matrix. It's a 2 by 2 matrix. All the entries are real numbers. And it says that when I add all those entries together, it's less than or equal to 0. Okay, interesting. So let's take a look at a couple of examples to get a feel for, what types of things are in H and what's not. So I got two matrices here. These are both in M 2 by 2. They are both 2 by 2 matrices. They're both in M 2 by 2. But now, are they in H? To check it, well, all their entries are real, so that's good. I got to add up their entries and see if I get something less than or equal to 0. So if I add up these entries, I'll get 2 plus 0 plus negative 3 plus negative 4. That's negative 5. Oh, and that is less than or equal to 0. Cool. Check mark. It satisfies that condition, which means this first matrix, well, this is in H. What about the next one? If I add these entries, I'll get 1 plus 2 plus 3 plus negative 4. Well, that ends up being 2, and that is not less than 0. So I'm going to put a sad face. That is not less than 0. So as a result, this one is not not in H. Okay, all the entries have to add up to something less than or equal to 0 to be in H. Okay, so I want to give you some time to try this on your own first. Again, pause the video for about 2 to 3 minutes to try this. 4, 3, 2, 1, pause it, and try it for about 2 to 3 minutes. All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it. So it'll turn out that this one is not a subspace. To show something is not a subspace, I just have to find one property that doesn't work. So, I could go in order like I did here and eventually find one that doesn't quite work. Or, if I have a suspicion, I might try to go straight to that first. So it turns out that, if you look at the 0, if you first ask yourself the question, is 0 in H? Maybe let's just ask ourselves that question. Is 0 in H? Well, what do we mean by 0 here? It'd be the 0 matrix. Here's the 0. The 0 matrix. Well, is this an H? Well, yeah, if I add up all the coefficients, add up all the entries, 0 plus 0 plus 0 plus 0, well, that is 0. And that does happen to be less than or equal to 0, like I need it to be. So it is an H. So this is an H. Okay, so that property isn't going to fail. That property holds. So what property might not work? Okay, it turns out we can try to find a problem with this closure under scalar multiplication. So let's check closure under scalar multiplication. Closure under scalar multiplication. If I take an example of something that's an H, like this, notice that the matrix 2, -3, 0, -4 is an H. We already explained why up here, so I won't do that again. Can I multiply this by some scalar so that the end result will not be an H? So I want you to pause the video one more time for about 1 minute to think about that if you didn't quite reach an answer earlier. So pause it in 4, 3, 2, 1, pause it and try this. Okay, all right, let's talk about it. Okay, so it turns out if you pick anything negative for the scalar, it'll end up doing the trick. Like if I pick C to be -1, and now I multiply them, C times my matrix, 2, -3, 0, -4. You know what, let me just go ahead and write that here. This is going to be -1 times the matrix. That is C. Well, it'll switch the signs of the entries. -2, +3, 0, +4. But now if I add the entries, what do they sum to? The entries sum to +5. Oh, and +5, well, that is not not less than or equal to 0. So it doesn't satisfy this condition. Thus, that means C times my matrix, what was it, 2, -3, 0, -4. Well, that is not in H. I'll put a slash through that. That is not in H. Okay, this violates this scalar multiplication property. So as a result, this means it is not a vector, not a subspace. Not a subspace. Since it's not closed under scalar multiplication. All right. It turns out if you were to check the addition property, that one would work. That would be a great practice problem for you to try that. But at this point, we know it's not a subspace, so that is good enough for us. Okay, let's do one more practice problem here in this video. Again, V is, this time it's going to be M 3 by 3, the vector space of all 3 by 3 matrices. And H this time says, well, what are the things in H? A is in M 3 by 3, so we're talking about 3 by 3 matrices. The colon means such that A is not invertible. So in other words, H consists of 3 by 3 matrices that are not invertible. Let's look at some examples to get a feel for what things are in H and what's not. So in this first matrix, is it invertible or not? Well, this has pivots in each column and row, so it is invertible. I'll just write inv. The next matrix, well, the pivots are just this one and this -3. So there's no pivot in the third row. There's also no pivot in the second column. Not all columns and rows have pivots. So this one is, I'll put it in red. This one's not invertible. Okay, so so if it's not invertible, that means it is in H. That's what the definition of this set says. It's consisting of non-invertible matrices. If it is invertible, like this first one is, well, then that would not be an H. Okay, so we are working with matrices like this second one, things that are not invertible. Okay. All right, so I want to give you all some time to try this. We want to ask ourselves now, will this satisfy those 3 properties? So pause the video for about 2 to 3 minutes again to try this. 4, 3, 2, 1, pause it, and try this one. Okay, that pause and trying is especially important on these subspace problems. This is a new type of problem I wouldn't expect you to have seen before in previous math classes. So getting that practice is really valuable, especially now, even when it comes before you get to trying those homework problems. Okay, so let's talk about it. So, I could go through the list of all 3 and, kind of think about them, but it turns out this is not a subspace, and I'm going to point out a property that doesn't work. So let's check closure under addition. I skipped talking about the 0 thing, but that's pretty quick actually. If I were to think about the 0 matrix that just has zeros everywhere, well, that would not have any pivots. And if it doesn't have any pivots, it's not invertible. And if it's not invertible, that is an H. So the 0 matrix is an H. So if it's not going to be a subspace, it's one of the other things that won't work. Let's check closure under addition. So if it wasn't going to be closed under addition, what we would want is to find 2 of these non-invertible matrices that I could add together. So I want this one to not be invertible, because if it's not invertible, it's in H. I want this one to not be invertible. But if I can find an example where the end result is invertible, well, if that was invertible, then it wouldn't be an H. Then this thing would not be an H. And that would show that it violates this closure under addition. Okay, so if you were a bit stuck earlier, I would again encourage you to pause the video and to try this. My one hint when you try to brainstorm these non-invertible matrices is it's really helpful if you can come up with examples where it's already in echelon form and you can already see the pivots. So do a quick pause for about a minute. 4, 3, 2, 1, pause it and try. All right, so hopefully you did that. Hopefully you paused it and tried it. So there are a bunch of examples. So I need something that's not invertible first. So maybe I'll just do something where I just got 1, 1 and all zeros. That's only got 1 pivot. So it definitely doesn't have pivots in all the rows and columns. What's something that I could add to it that's also not invertible? But I want the end result to be invertible. Well, I need this end result to have pivots in every row and column. So I need this second matrix to kind of give me those missing pivots. So maybe I'll try to make this bottom right corner be something, like maybe I'll let this be 3. Maybe I'll let this be like -5 here. I don't know, the numbers don't really matter as long as I pick non-zeros there. And maybe over here I pick zeros everywhere else. Okay, this second matrix still doesn't have pivots in every row and column, though it's not invertible. And when I add them together, I'll get 1, -5, 3 on the diagonal, zeros everywhere else. And now we got an example. The first two matrices are not invertible, but when I add them together, it is invertible, so it's not closed under addition. Okay, thus, it is not a subspace. Since it's not closed under addition. All right, that is our answer. I guess maybe one important thing I should add in my explanation, this would be important to do, especially if this is a homework or a test, is give reasons for why these are not invertible. Not all rows plus columns. I said it in words, but we didn't write it down. Not all the rows and columns have pivots. So that's the reason for why these are not invertible. And well, why is this one invertible? Because all the rows plus columns have pivots. That makes this one invertible. All right, there we go.